We will discuss about the graph traversal in this lecture. Suppose there is a graph given and we have to traverse this graph. So traversal means the exploration of each of the vertex in the graph, and we need to find out in what sequence I can traverse this graph. Now there are two techniques by which the traversal can be done in this graph. One is the breadth first search. It's also has a short name, BFS, and the another way is depth first search. It also has a short name, DFS. So let us first discuss the breadth first search, BFS. For this I need to write down the adjacency list. So adjacency list is very simple. You just mention the name of the vertices, and then the connections. I'm writing it in a short form. I'm not making all the notes. It's just a short form of the adjacency list. So this is the adjacency list that I'm forming. So from A there are two connections, B and H. I should write these two in the alphabetical sequence. From B we have the connections A, C and H. From C we have the connections B, D, F and I. From D we have the connections C, E and F. From E we have the connections D and F. From F we have the connection C, D, E and G. From G we have the connections F, H and I. From H we have the connections A, B, G and I. From I we have the connections C, G and H. So for doing the graph traversal using BFS, I need to have a queue. Now the queue has a size the same as the number of vertices. In this graph we have 1, 2, 3, 4, 5, 6, 7, 8 and 9 vertices. So the size of this queue will be 9. It means it should be able to accommodate 9 elements. In this graph I consider that every vertex can be there in 3 of the states. One is the state in which it is not explored. The other state is it is explored and there in the queue. And the third state is it has got deleted from the queue. So there are the 3 states in which I can think of my vertices in. One is the state in which it has not been explored. So I can think of that this color is white. It means I am coloring the graph, coloring the vertices of the graph, and the first color is white in which none of the vertices has got explored. The case in which a vertex has got explored and there in the queue, we will say that this is of gray color. And then if a vertex has got deleted from the queue, it is of black color. Fine. So we are considering that a vertex can be there in 3 or either of these 3 colors at any given point of time. Initially we consider that every vertex is of white color. Now I keep or I insert the vertex A in the queue. Since it's there in the queue, its color will be gray. Now I explore all the vertices going from A, means from the front vertex. What are the connections? So connections are B and H. So the color of B and color of H both are white. Let's do the color of these two vertices as gray and keep it there, insert it there, and queue these two in the queue. Delete A and consider that this has been added in the BFS sequence. And then pick the next vertex in the queue, that is B. See all the connections from B. These are A, C and H. Out of A, C and H, vertex A is having color black. Obviously it has got deleted from the queue, so its color will be black. I forgot to do that in the earlier step. So its color is black, so it cannot be kept again in the queue. A vertex can be kept in the queue only if its color is white. So we cannot keep A in the queue. Now C has a color white, so let's make its color as gray and insert it in the queue. Now for H vertex, it has a color gray, so I cannot keep it in the queue. So only vertex which has got inserted in this step is C. So we have seen all the connections from B. So let us delete B and add it to the BFS sequence while making its color black. Next vertex in the queue is H. So let us see all the connections from H. These are A, B, G and I. So A color is black, B color is black, G color is white, so I can add this in the queue. Let's make its color as gray. I, it's of white color, let's make its color as gray and insert it on the queue. We have seen all the connections from H, so delete H, add it in the BFS sequence and make its color as black. Now see the connections from C. So from C we have the connections B, D, F and I. B has a color black, D has a color white, so add D here and make its color as gray. F of color white, make it gray and insert it at the queue. I is of gray color already, so we will not add I here again. So we have seen all the connections from C, delete it from the queue, add it in the BFS sequence and make the color of C as black. Next we have G. See all the connections from G. F is of gray color, H is of black color, I is of gray color, so we cannot add any of these three vertices. So delete G, add it in the BFS sequence and make its color as black. Next vertex is I. See the connections from I. It has a connection C, G and H. C has a color black, G has a color black, H also has a color black, so none of these vertices will be added in the queue. So we are done with I. Delete I, make its color as black and add it to the BFS sequence. Next vertex is D. Let us see the connections from D. These are C, E and F. So C has a color black, E is of white color. So since this is of white color, make its color as gray and add it to the queue. So we are next vertex is F, which is already of gray color. So delete D, add it to the BFS sequence and make its color as black. Next vertex is F. C, D, E, G are the connections from F. C, D, E, G, all these vertices are of black color. Sorry, C is of black, D is of black, E is of gray color and G is of black color. So obviously we cannot add any of these four vertices in the queue. So just remove F, add it to the BFS sequence and make its color as black. Now from E we have the connection D and F. The color of these two vertices are black, so we cannot add these two vertices in the queue. So remove this E, add it to the BFS sequence, and make its color as black. So now you can see that we have got this sequence. So this is the BFS sequence. We have explored the vertices in this sequence. So while doing the BFS, what we have done, we have started with the color of vertices color, and the color of each of the vertex has been set as white. If I am inserting any vertex in the queue, its color will be black. Sorry, its color will be gray, and if I am deleting it from the queue, its color will be black. So a vertex can be inserted in the queue only if its color is white. While adding it into the queue will make its color as gray. Right? So let us now write the algorithm for the same. So the very first thing that we are doing in this is defining that we are writing the BFS. A graph is given, and let's say a source vertex is also given. The source vertex here in this graph was considered as A. Not the source but the root actually. Let's say this is the root. So from where we are starting is the root. So let's say that is given. In case that is not given in our questions, we will consider the alphabetical sequence, the first vertex in the alphabetical sequence as the root. If the numbers are given on the vertices, then the number which is coming as first will be the root. Now in this BFS algorithm, we will have to assign the colors to the vertices. So let's say for all u, that is element of vertices of the graph. So if this graph is given, we will consider that Vg is representing the vertices of graph, and similarly Eg will be representing the edges of the graph. So for all vertices in the graph, you have to initialize the color of these vertices as white. Let's say there is a color array, and the color array will be containing the same number of entries as that of the vertices. So color u is white. Fine. Let us take a queue. Let's say we are taking a simple queue Q, and let's say we are initializing this queue. Obviously we will have to initialize this queue. Initializing means initially we should ensure that there are 0 elements in this queue. Then what we will do, we will enqueue the root vertex in this queue. So in this queue we are going to insert this root vertex R. Let's say there are two parameters. First one is the queue and the vertex to be inserted. Obviously if you are inserting this vertex in the queue, then the color of this vertex should be gray. So we have said that this color is gray. And then you see that in the algorithm what we did in the question, we were doing our operations by the time my queue does not become empty. So by the time there are the elements in the queue, we were doing the operations. The moment the queue has become empty, we will stop our operation. So here too, while writing the algorithm, I will ensure that I will do the activities only if my queue is not empty. So if my queue is not empty, what I will do, I will remove the first element. Let's say I am removing the first element by the operation dq. So with the dq operation, I have removed the element, and let's say that vertex is u. Now I will see all the connections from u. Let's say this is the u. I will see all the connections from this u. So for all u, all v, let's say, that is adjacent to u. Let's say there is an adjacency list. If a graph is given, obviously the adjacency list is available. So U is the vertex which has got deleted from the Q. So this vertex, we will see all the connections from U one by one. So let's say the first connection which I have seen is V, and if the color of this vertex is white, this is our target vertex. So if the color of this vertex is white, then what I'm going to do, I'm going to insert this in the Q. So NQ V vertex, and make sure that its color is gray. So what I did, I have removed a vertex from the Q. We have seen all the connections from this U. So all the vertices which are adjacent to U, if their color is white, then they will be added in the Q. And while adding it, I will ensure that its color is gray. Now once I have seen all the connections, I will make the color of U vertex, the vertex that I have deleted from the Q, as black. Color of U as black. And if I have to display the vertex, then I will write this vertex U, because this is the first vertex that I have explored. Fine. So the order in which the deletions are taking place, the same is the order of the BFS. Fine. So this is the algorithm. So let me write a keyword algorithm here. We'll begin here and we will end here. So once again, let's see this algorithm. For all the vertices in the graph, what we are doing, we are initializing the color of that vertex as white. Unexplored vertices will have a color white. Let's take a Q. Initialize that Q means initialize that there is no element in the graph, in the Q. We will insert the root vertex in the Q. While insertion, we will make sure that its color is gray. And by the time Q does not become empty, we will do some operation. The operation says that remove the first element from the Q, remove the front element from the Q, see all the connections from this vertex. If the vertex which is connected to U has a white color, then insert that in the Q and make its color as gray. So every vertex which is going to insert in the Q will have a color gray. And then once you have seen all the connections from this U vertex, make the vertex color as black and print this. Okay. So by the time Q is not empty, we will keep on deleting the elements. So this actually is the BFS. We will make some more changes to this BFS algorithm, because BFS is not only to ensure, not only to find the vertex sequence, it may be able to find some more things. For example, in the same example, let's take two more parameters. So I'm writing this Q again. Fine. So first we have inserted A, which is a root vertex. So let's make one more parameter. Let's take another parameter, which is, let's say, the distance. Fine. And let's say there is a concept of the predecessor also. So there are two more parameters here. One is distance and the other one is predecessor. It's not been written clearly. Let's write it more clearly. Predecessor. And this is distance. So obviously the distance from root to root will be 0. So that's why I have written 0 here. And let's say A has been explored automatically, so its predecessor is nil. There is no predecessor of A. Now from A, I have seen B and H. So B and H have got inserted from, B and H were explored from A. B and H are connections from A. Obviously B and H have got explored from A. So let's make the distance of B and H 1 more than the distance of A. So B has a distance 0. Let's make its distance as 1. The distance of H is also set as 1. So distance of B and H both are set 1 more than the distance of A. Since B and H have got explored from A, so the predecessor of B and H are also set as A. Fine. Now it will get deleted. And then we will see the connection from B. If we see the connection from B, then the connections are A, C and H. A has already got deleted from the queue, so obviously we will not be inserting it again because every vertex is going to get inserted in the queue only once. So for C, we will insert C here. For H, H is already there in the queue, so we will not insert it again. So we have, in this step, we have only added one vertex in the queue, that is C. Now this C vertex has got explored from B. So the predecessor of C is set as B. And distance of C is set 1 more than the distance of B. So distance of C is 2. Right? Now we'll delete B and we'll add to the BFS sequence. Let's take H. The connections from H are A, B, G and I. So vertex A has got inserted in the queue some time back. Similarly B also, so we will not insert it again. G and I, these vertices have not been inserted in the queue, so these two can be inserted. And now G and I have got explored from H. So the predecessor of G and I will be set as H, and distance of G and I will be 1 more than the distance of H. So distance of H is 1. The distance of these two will be set as 2. Now delete H and add it to the BFS sequence. Let's pick another vertex, that is C. So the connections from C are B, D, F and I. B was inserted in the queue some time back. D is not there in the queue, so let us insert D. F is also not there in the queue, so let us insert F. I was inserted some times back, so it will not be inserted again. So now this D and F have got inserted with the help of C. So the predecessor of D and F will be set as C. And the distance of these two vertices D and F will be set as 1 more than the distance of C. So the distance of C is 2, so distance of D and F are been set as 3. Remove C, add it to the BFS sequence. Let's pick another one, G. Connections from G are F, H, I. F is there, H is there, I is there, so no connection will be added in the queue here. Delete G and add it to the BFS sequence. Now for I, connections are C, G, H. C is here, H is here, G is here. No connections will be added from here. So remove I and add it to the BFS sequence. From D, C, E, F. C is already there. E is not there. So let us add E here. F is already there. So E has got explored from D. So the predecessor of E is set as D. And the distance of E is set as 1 more than the distance of D, which is 3. So 3 plus 1 is 4. Delete D, add it to the BFS sequence. Then from F, the connections are C, D, E, G. C is there, D is there, E is there, and G is also there. So no more connections will be added in the queue. Delete F and add it to the BFS sequence. From E, the connections are D and F. D is there, F is there, no more connection will be added in this queue again. So E is removed and added to the BFS sequence. So after doing so, what we have achieved, if you see, if we form the vertices only in here, A, B, C, D, E, F, G, H and I. Then just see this predecessors. So A has no predecessor, B has a predecessor B. So draw an edge AB. Similarly, draw an edge AH. Draw an edge BC. Draw an edge HG. Draw an edge HI. Draw an edge CD. Draw an edge CF. Draw an edge DE. Fine. Now see, distance of root to root is 0. Distance of A to B is 1. Why 1? Because there is only one edge involved in between. Distance of A to H. Look at this one. Distance of A to A is 0, A to B is 1, A to H is 1. A to H. Only one edge is involved here from A to H. 1. For C it is 2. You can reach from A to C by this path. A to B, then B to C. 2 edges are involved. So the distance is 2. Similarly for G it is 2. Why 2? A to H and H to G. For I it is 2. A to H, H to I. 2 edges. For D it is 3. Path is A to B, B to C and C to D. 3 edges are involved. For F it is 3. So A to B, B to C and C to F. 3. E to D. E has a 4 distance. So the path is A to B, B to C, C to D and D to E. It has a length 4. So this BFS has not only resulted as the sequence of the vertices, but it has resulted us in the shortest distance also. If the cost of all the edges are assumed to be 1, then we are finding the shortest distance also here. You can see that this graph that we have achieved with the predecessor does not have a cycle. So we can say that this is a tree graph, and we say that this is a BFS tree. So BFS algorithm has resulted as in 3 things. One is the BFS tree, another one is the BFS sequence, the sequence in which the vertices will be explored, and it will be telling us the shortest distance between the defined source. Why we are saying the defined source? Because the root is fixed. So we are finding the shortest distance of all other vertices from this root. So this is telling us the shortest distance. Fine. Let us make these corrections in the algorithm also. So while initializing, we can say that the distance of the root vertex is set as 0. Fine. And let's say while initializing, we are ensuring that the predecessor of every vertex is set as nil, and then it will be updated while doing the exploration. So we are taking 2 new parameters here. One is the pi, which is representing the predecessor, and d, which is representing the distance. So distance of root is set as 0, and we consider that initially there is no predecessor of any node. So pi of u equals to nil. When we are exploring the vertices, the first vertex that I have removed from the queue is u, and then we are seeing the connections from u. The connection that we see, we are seeing if v vertex is connected to u and it has a color white, then it is added in the queue. So while adding it in the queue, we are setting up 2 parameters. The distance of v is set as 1 more than the distance of u. So distance of v is set 1 more than the distance of u. At the same time, I am setting up the predecessor of v as u. Why? Because V vertex has got explored from U. So the predecessor of V is set as U. Fine. So we have set two new parameters, predecessor and distance. And with the help of the predecessor and the distance, I can draw this BFS tree in which we can see that the shortest distance is also mentioned. Thank you.